It is a great pleasure to introduce our SuperMUC NG project to you, together with my postdoc Robert Bollig. And the project is concerned with 3D simulations of core collapse supernovae, and the particular question how they evolve from 3D progenitors to the state of energy saturation during the explosion. The team consists, besides of Robert Bollig and myself, consists of Naveen Yadav, a postdoc, and PhD student Daniel Kresse. We also have external collaborators Bernhard Müller and Alexander Heger at Monash University in Melbourne. We are interested in objects like these, in phenomena like these. This is famous supernova 1987A, when on 23rd of February 1987, a blue supergiant in the Large Magellanic Cloud exploded and within days gained billions of times its pre-explosion brightness. And the supernova is still visible nowadays, and we can follow online its evolution as a young supernova explosion. Supernovae in the past have left remnants in our own galaxy, which we can observe. We have more than 200 of them. Here's a famous example. The Crab Nebula, the relic of a supernova, exploded in the year 1054 at a distance of about 5,500 light years. And another famous example is seen here on this slide, the Cassiopeia A supernova remnant at about twice this distance. And this supernova is close to 400 years old. And also in this case, the relics, the debris of the exploded star expand highly asymmetrically into circumstellar space. The phenomenon of supernova explosions, their evolution, is sketched on this slide, where you see the so-called onion shell structure of progenitor stars after some tens of millions of years of evolution. And prior to collapse, they have evolved an iron core, which is zoomed out in the lower left part. This iron core has about the size of the moon. And when it reaches a limiting mass close to the Chandrasekhar mass, particle physics processes set in, and within less than a second, the core collapses to a neutron star, and a shockwave is launched, and the shockwave explodes the supernova. The relic neutron star is initially very hot. It radiates neutrinos intensely, and over several seconds, this hot extended neutron star, initially with a diameter of about 100 to 200 kilometers, this neutron star contracts and cools to the cold object with a diameter of only about 20 kilometers. The supernova explosion itself is one of the main questions. What is the mechanism behind this supernova? And on this slide, you can see the paradigm of the explosion mechanism, which has been a theoretical concept for more than 50 years, until very recently, three-dimensional simulations with detailed treatment of neutrinos demonstrate the viability, and our simulations here on SuperMUC have been the first ones demonstrating the viability of this mechanism. The hot neutron star radiates intense neutrino fluxes, and some of these neutrinos get absorbed in the material behind the shockwave, depositing their energy, and this energy deposition then pushes the shock outwards and launches the explosion. So neutrinos trigger and power the supernova explosion. The input physics has a high diversity. It's a multi-physics problem. We need to deal with the hydrodynamics of the stellar plasma. We have to treat relativistic effects, general relativity in particular. We have to describe the plasma thermodynamics inside of the hot medium of the neutron star at high densities, but also in the dilute surface layers of the progenitor star. We have to treat neutrino transport and neutrino matter interactions, and we need initial conditions, which are provided to us by stellar evolution modelers. And all this combined into a dynamical model allows us to predict the multiple observables, which we want to connect to measurements and to astronomical observations. The problem is connected, one of the problems is connected to the progenitor models, because these models are given to us as ideal spherical conditions, as shown here on this slide. we actually get the progenitor star in its onion shell structure in a one-dimensional model. But in reality, and here we zoom now in to the central part of this star, in reality, we already have in the progenitor star prior to its collapse, three-dimensional large amplitude and large-scale perturbations. And these perturbations are connected to the convective oxygen and silicon shell burning. And it has turned out that these asymmetries have a big influence on how the explosion starts and how it develops. This poses a timescale problem for us because we need, on the one hand, to go backwards in time from the onset of collapse, which is marked here by a vertical dashed line. We have to go backwards by at least several minutes or even hours in order to follow the latest stages of the convective shell burning to create the initial conditions in 3 dimensions. But we also need to go forward in time in order to connect explosion models, models which explode due to neutrino heating, with astronomical observable supernova properties. And this forward timescale is days, weeks, months actually into the developing supernova. Most of the existing 3D supernova simulations and all of the detailed ones with all the microphysics are concerned only with a short phase in this evolution, namely about from the onset of the core collapse to the beginning of the explosion. Our project extends in both directions, backwards in time, but also long periods of time forward into the supernova explosion. This also poses a challenge of radial scales. The onset of the explosion, the mechanism itself, takes place in the innermost central region of the star with a diameter of a few hundred kilometers, whereas the whole star has an extension of tens of millions, if not hundreds of millions of kilometers. So we have to progress forward from the innermost region to the outermost layers of the star and follow the whole evolution. Our project was motivated by the following questions. How do pre-collapse progenitor asymmetries influence the supernova explosion? What are the effects of muon formation in hot neutron stars on the supernova explosion? Muons are particles which are formed in the hot neutron star medium, and their formation, which is undisputed actually, this formation has never been accounted for in supernova models. Can the neutrino-driven mechanism explain explosion energies and other observables of core collapse supernovae? Let me summarize here on this slide the main achievements of our Gauss and LRZ projects. SuperMUC NG has enabled us to do the most sophisticated and physics-wise and numerically most comprehensive 3D supernova simulations over the longest evolution periods carried out to date. We have the first simulations of pre-collapse convective oxygen shell burning, continued over several minutes. We have the first ab initio self-consistent 3D supernova simulations until 7 seconds with the achievement of a saturated explosion energy. We have done the first 3D supernova simulations, including muon physics, and we have the first long-time simulations of self-consistent supernova models until several days. Let me now show you some highlights of our results on the next couple of slides. And I first start with the 3D simulations of convective oxygen and neon shell burning in a 19 solar mass progenitor. Here are results from Bernhard Müller and Naveen Yadav. And instead of describing to you the plots here in detail and the progenitor asymmetries prior to collapse shown in these plots, let me play a movie to demonstrate the phenomenon. What you see here is color-coded the radial velocity in this convective oxygen layer. It's visualized here by an ISO surface of a constant mass fraction of silicon. In the top right corner, you see the time progressing. And after about 5 minutes in this simulation, we already have large-scale asymmetries developed by this convective oxygen shell burning. We continue further towards the onset of core collapse, and now a neon oxygen shell merger leads to large-scale asymmetries and large-scale flows which already perturb the progenitor before the core starts to collapse. This defines the initial condition for a continuing simulation, which was carried out by Robert Bollig, where he simulated the core collapse and explosion of this 19 solar mass star. And what you see here on this slide in the upper left corner is the so-called mass shell plot, where at the center you see the neutron star forming, and here the shock wave is revived in this explosion and is pushed outwards due to neutrino heating. The upper right plot shows the neutrino luminosities and the neutrino mean energies as function of time during this simulation over 7 minutes and 7 seconds. And in the left lower corner, you see that the explosion develops highly asymmetrically. You see times of 0.5 seconds, 1.7 seconds, and 7 seconds. And we followed the explosion into the phase where we finally saw the explosion energy saturating at a level of about 10 to the 44 joule, which is 1 beta, and it's a healthy, viable explosion energy of supernova. Let me demonstrate by a movie an important finding, namely that none of our simulations starting with spherically symmetric initial conditions as provided by stellar evolution modelers exploded. We only obtained explosions when we used our 3-dimensional initial conditions, which we computed by this convective oxygen shell burning. And you can compare the two situations here. The left is the exploding model starting with 3D conditions. The right is the non-exploding case in a 1-dimensional progenitor. And you see that the left explosion sets in. On the right, we stopped after a certain while because the star definitely did not show any indication of exploding. And on the left side, with the 3-dimensional initial perturbations, we see a violent supernova outflow developing. Let me very briefly flash the main results of our project on the impact of muon formation. Muons in the nuclear medium actually lead to a stronger contraction of the neutron star. The neutron star becomes hotter. For this reason, it radiates higher neutrino luminosities and mean energies, and the explosion can therefore set in earlier. And you see this here by comparing 2 and 4-degree runs without muons with a 4-degree run where muons were included, while the two simulations without muons explode later. The case with muons explodes significantly earlier. Unfortunately, we could not rerun the model with 2-degree resolution because including the muon physics is very expensive because of this additional physics needed. And finally, let me also flash you a couple of results for our long-time supernova simulations, here in this case of low-mass progenitor stars, where we evolved a set of stars with masses at around 9 solar masses from the onset of the explosion to late stages. In the lower part, you see the result of for 3 times of a 9 solar mass simulation. The left plot shows the asymmetric explosion after about 4 seconds. The middle plot shows the same explosion after 12 minutes. And on the right side, you see the situation after close to 3 days. And you see this explosion developing highly asymmetrically. And the explosion parameters we found in this 9 solar mass simulation here listed in the upper right part of this slide are very well compatible with this famous remnant, which I already mentioned, namely the Crab supernova, which is a sub-energetic explosion of about only less than 1/10 of a beta. And also the nickel mass in this explosion was diagnosed to be very low. And these parameters, these observables, including the neutron star properties, are well reproduced by our simulations. Our project already led to 3 major publications listed here on this slide, but there's more to come. Currently, we write a paper on the muon results, and so I ask you to stay tuned. And now for the methodical implementation of our project and the details on that, I hand over to my postdoc, Robert Bollig, who will describe this part of our project.
Thank you, Thomas, for this nice overview of our project. I will now go into further detail on the implementation and numerics that made these results possible. First, a small overview of the code we use for our simulations. Prometheus is the hydrodynamics module that implements the explicit finite volume piecewise parabolic method with an exact Riemann solver, Newtonian self-gravity with effective GR corrections, and an axis-free overset yin-yang grid that avoids the problematic CFL criterion around the polar axis. Vertex is a neutrino transport module that implements an implicit spectral two-moment scheme with a variable Eddington factor closure computed by a model Boltzmann equation. The neutrino moment equations themselves are formulated in the ray-by-ray plus approximation, which means we assume purely radial propagation of neutrino energy. The plus part means we still include lateral neutrino advection with the medium and non-canceling lateral pressure terms. Of course, the neutrino matter interaction terms are an important ingredient, and we implement the most comprehensive set of neutrino interactions in our field. Now a small summary of the neutrino transport equations we solve in each time step. The Boltzmann transport equation is the kinetic equation for the radiation intensity at a specific point in space into a specific propagation angle. This makes the Boltzmann transport equation a 6D equation with 3 spatial and 3 momentum coordinates. In our spherical source approximation, the Boltzmann transport equation reduces to a 5D equation, in which only the angle cosine mu between the ray normal and the neutrino propagation direction is kept. The Boltzmann transport equation contains both angular derivatives on the left side, as well as angular quantities in the collision integral on the right side. This makes the Boltzmann transport equation an integral differential equation, which is particularly difficult to solve. Instead, we couple the left side of the Boltzmann transport equation with the moment equations of the radiation on the right side, and iterate both equations until convergence is reached. The evolution equations of the angular moments are called the moment equations. Here, the zeroth moment can be identified to be the neutrino energy density J. The first moment is the neutrino energy flux density H, and the second moment is the neutrino pressure density K. In the equation for the zeroth moment, you can see higher order terms. Similarly, in the first moment equation, you see that it needs both the second and third moment to close the equation, which are not calculated in our two-moment equation set alone. Instead, these higher normalized closure moments are calculated from the Boltzmann transport equation, the so-called variable Eddington factor closure. For completeness, on the right side is a list of all the neutrino interaction rates that have been used in simulation runs of this project. As the neutrino transport part is the most expensive part of each run, it is not economical to use the highly detailed transport where it is not strictly necessary. Therefore, after a certain point, when we are sure that the dynamics of the explosion are relatively fixed, we turn off vertex and switch to a simplified light bulb-like scheme. For this, we assume a spherical neutron star with spherical neutrino emission. The heating and cooling terms are then derived from local gas quantities and neutrino field quantities imported from a 1D source. This 1D source is taken from a prototypical 1D protoneutron star cooling simulation that has been specifically set up to be a best fit for the protoneutron star mass and energy content evolution of the 3D simulation. In comparison to older simulation runs on SuperMUC, we have further improved our modeling on SuperMUC NG. We have improved our spectral resolution from 12 to 15 energy bins, which increased the average work by 50% per transport time step. We further added a small alpha chain nuclear reaction network that added about 25% more work per hydro time step, with many tens to hundreds of explicit hydro time steps needed for each implicit transport time step. Third, we have added muonic physics into a part of our model runs, which further increased the overall effort spent by another 200%, as we now need to simulate the full 6 flavor space, rather than the simplified 3 neutrino flavors of our normal runs. As can be seen on the plot on the right, we've managed to utilize the new LRZ hardware sufficiently well that we are able to perform 4 times longer simulations, needing about twice the number of time steps, but requiring less core hours overall than required on the old SuperMUC. But the new SuperMUC NG also posed some challenges. The new Skylake processors offer more cores per node, which meant we needed to increase the OpenMP parallelization of our code. As they are more coarse, but not significantly more memory bandwidth, the reduction of memory accesses is becoming more and more important. Furthermore, the new AVX512 vector units meant that special optimization work needed to be done on every loop in the code to get good vector performance, augmented by explicit directives where necessary. An overlook over the individual phases of a single time step is shown below. The communication-bound, compute-bound, and memory-bound phases of the code are clearly visible, as well as the iterative nature of our coupled Boltzmann equation set. Our overall parallelization strategy is the hybrid MPI OpenMP approach with an increased focus on vectorization. We decompose our computation domain into angle blocks via MPI with direct next neighbor communication. The individual angles are then distributed by our coarse intra-block OpenMP parallelization. To further increase the degree of parallelism, we have also introduced a nested fine parallelization that distributes the neutrino energy bins to the closest available processor. Vectorization then takes care of the remaining fastest moving spatial coordinate, which is the angle cosine mu in the Boltzmann transport equation and the radial coordinate in the interaction rates and moment equations. But of course, the largest payoff of any optimization work is gained by algorithmic improvements. In our case, we use a radial staggered grid discretization in which radiation energy density is stored on cell centers and radiation flux density is stored on cell interfaces. The divergent term used in our equations are then simple central finite differences. It is, however, known that central difference is unstable at steep discontinuities, which is why we use artificial diffusivity terms of first order to tame discontinuities in the radial neutrino field. However, we found that discontinuities in energy space caused by Doppler shifts are not corrected by these diffusive terms, as they are not formed by the neutrino time illusion themselves, but rather by the background velocity field. Only the modifying the neutrino diffusivity was then not enough. Our implicit backwards Euler time integration is unconditionally stable and so was able to keep the simulation running, but the instability led to the constant emission of wave packets. The benefit of implicit solutions are that they converge very fast for solutions striving towards a steady state. However, they lose most of their effectiveness when solving for highly non-stationary wave solutions, which require increasingly high time resolution. We have identified a simple approach to tame the problem by artificially smoothing the mapped velocity field on the transport grid, therefore spreading the shock velocity jump over more radial zones, as shown in the plot below. This improvement has been fundamental for the project's success, as this has allowed us to reach into the post-explosion phase with up to 10 times longer time steps and better convergence than before. The memory bandwidth optimizations are another major point, as our code, as most stencil codes, is heavily bandwidth limited. Our Boltzmann transport equation decomposes into a large set of quasi-independent pentadiagonal band matrices. The traditional way to solve such banded matrices is to use a Thomas algorithm, shortened to TDMA, which we have parallelized using OpenMP. We further employ a compact storage matrix format in which we vectorize over the independent angle cosine mu, making the matrix a 3D tensor. This calculation is very efficient, requiring only an order of n operations per solve, but is highly bandwidth limited, as there are only very few flop per byte of data. In total, the entire matrix is about 15 gigabytes in size and needs to be solved multiple times per transport time step, which means we quickly saturate the full memory bandwidth. The traditional way of solving such a matrix is that one first calculates and fills all elements of matrix A, and then gives that to some standard solver. This, however, means we need to write the full matrix to memory first, then give it to the solver, which then needs to load the entire matrix again. This destroys any caching advantage. Instead, we now make heavy use of the spatial locality of the Thomas algorithm, as it has a compact, well-defined stencil. It turns out that each intermediate result of the forward solve of algorithm only requires the matrix element at its current diagonal position, plus the previous 2 iterations of the intermediate result. The matrix elements themselves are local values along the radial coordinate and have a simple algebraic relation on angle cosine mu and can be calculated in place. This means we can reduce the entire memory bandwidth of the forward solve to a single store of the 3 work bands needed for the back substitution, with most of the loads handled in cache. We can further make use of additional sparsity of the top and bottom bands, as the pentadiagonal matrix can reduce to an alternating tri-pentaband configuration at alternating radial coordinates. The speedup of the Boltzmann transport equation solution has been significant, at a roughly 4 times improvement. Nonetheless, we still saturate the memory bandwidth. This, in combination with the easily vectorizable structure of the matrix, makes it an ideal candidate for future offloading to an accelerator. A similar problem structure is seen in the moment equation, in which pentadiagonal and block matrices need to be solved. In these matrices, each of the band elements is itself a 2Ne by 2Ne matrix, as the neutrino species and energies are now fully coupled. This means that all scalar multiplications become a degem operation, and the division becomes a matrix inversion. The problem we have is that standard linear algebra libraries are optimized for very large matrices, more than 1,000 by 1,000 in size, which makes the overhead for small matrices quite measurable. An improvement we have recently implemented is to use the MKL JIT just-in-time small matrix degem kernels, which are highly optimized for smaller matrices less than 100 by 100. Furthermore, we can replace the Thomas algorithm with a parallel cyclic reduction algorithm, which however requires about 3 times more operations than the serial Thomas algorithm. This makes it only worthwhile to use when more than 4 nested threads are available. In terms of the parallelization efficiency, we've already demonstrated perfect MPI scaling of Prometheus vertex at a previous LIZ extreme scaling workshop. We have now also spent more work at improving the intranode scaling using our nested OpenMP implementation. The takeaway here is that the compute-limited parts of our code benefit the most with nearly linear scaling. However, the memory bandwidth-limited parts still lag behind. This is also a consequence of the moment equation block matrix solver being inherently scalar, and the cyclic reduction only reaching parity at 4 cores and beyond. This leads to a performance gap between 1 and 4 cores. What is remarkable, however, is that hyperthreading can lead to a significant speedup, as shown by the slightly offset blocks at 1 and 2 physical cores, as the CPU can now overlap memory stalls with computation. The vectorization of the entire code has been quite thorough, resulting in about 80% of all flops being vectorized, with the rest mostly made up of matrix transposes, which we are still struggling with. However, as the scaling plot on the right shows, we still can't fill the large AVX512, which is just fast enough, so some headroom still remains. The sum product of all these optimizations have been the full model set shown here, with the red lines separating the muonic models from the standard setups above. To summarize, in this project, we've simulated 16 full 3D core collapse supernova models, leading to 8 successful explosions. We have simulated 8 4-degree models on 5,000 cores sustained, 7 2-degree models on 16,800 cores sustained, and our first attempt at 2 1-degree resolution models running on 54,000 cores. In total, we've consumed 190 million core hours, which yielded the first self-consistent 3D model to reach an explosion energy of 1 beta, equivalent to 10 to the power 51 erg. And we've simulated the first self-consistent implementation of muonic physics into the 3D core collapse supernova case. And my last advice to all the people struggling with the code's performance is to make good use of the LIZ and PRAISE workshops, because I've found them to be tremendously helpful, and I'm sure they can be helpful to you too. So now I am appreciating your time, and I'm awaiting the questions. Thank you very much.